Hi guys. Okay, so in this video, we are looking at the attractive forces in the molecule, and these are also called the intermolecular forces. Okay, intermolecular, as the name states, is the attraction between the two different molecules. Okay, so the two neighboring molecules, there are hydrogen bonding, there is dipole attraction, and then there is London dispersion forces, and these are also commonly called dispersion forces. Okay, so dipole attractions exist between polar molecules. So as you can see that one end of the molecule is polar and the other end is more electronegative than the other. Okay, so we see a dipole is induced in a molecule, and this dipole is like the more electronegative side, the electrons spend more time there, so that has a delta negative charge. Hydrogen in this, for example, HCl is less electronegative, so the electrons spend less time towards it. So that side will have a slight dipole, which is like a temporary charge, or it's like a very small charge, right? So that is the delta positive. Delta negative side on the chlorine is because chlorine pulls the electron clouds towards itself. It's more electronegative. Okay, so this is what's going on, and we see that these two polar molecules, the only thing is alignment. So when they are near each other, the negative end and the negative end will repel, but the negative end of one and the positive end of the other attract. And so this attraction is the intermolecular attraction or the intermolecular force. It's a very weak network that exists between the negative end of one and the positive of the other. So that is the dipole. So all you have to do is you have to look in the molecules, and you have to look at the like the difference in the electronegativity, and just determine if it is a polar molecule or not. If it is a polar molecule, yes, the dipole is going to exist. Now, sometimes in big molecules, one end is non-polar, the other end is polar. So, you know, like the ones that are organic molecules. So even in that one polar site, you know, so it's overall, it will be still a non-polar molecule. Okay. Next is the hydrogen bonding. Hydrogen bonding exists also between the two neighboring atoms, but the neighboring molecules. But here's the thing: nitrogen, oxygen, and fluorine. It only exists when hydrogen is attached to oxygen, nitrogen and oxygen are attached, and fluorine and hydrogen are attached. So it's the attachment of nitrogen, oxygen, and fluorine to hydrogen in a molecule, right? So what happens that this is an example of ammonia in which nitrogen is there. So this nitrogen, first of all, is attached to hydrogens, right? So if you look at that, so this hydrogen, less electronegative. So each of the hydrogens will have a delta positive charge. Nitrogen will have a delta negative charge because it's more electronegative, so polar bonds. Besides that, nitrogen also has the lone pairs. Now, the lone pair of one is attracted to the positively charged, this hydrogen of the neighbor. So it's always the lone pair on the central atom, you know, that influences all these things. So here you have this other nitrogen, hydrogens in the ammonia. So you see the neighboring nitrogen does not, the hydrogen is delta positive, but the neighboring nitrogen is delta negative, and the neighboring nitrogen has the lone pair on the central nitrogen. Okay, so this lone pair on the nitrogen, what does it do? It attracts the hydrogen of the, like a neighboring ammonia molecule. So the lone pair of nitrogen of one and the hydrogen of the other, they are weakly attracted to each other. So that bond is called a hydrogen bond. Okay. Now the same kind of bond exists between when there is water molecule, so or water, or when there is OH rather. So it's always the oxygen, the central atom. It contains lone pairs also. It's a bent molecule. You should draw the molecule, the Lewis structures, you will see. It's bent molecule and it has got lone pair on the central atom. Hydrogens, less electronegative. Oxygen, very electronegative. So that bond between hydrogen and oxygen is polar. So hydrogen being delta positive is now is unhappy. But this neighboring oxygen, which is already bonded to its own hydrogen, but it also has the lone pair. So what does it do? It lends its lone pairs temporarily to this neighboring hydrogen. And as a result, a very weak electrostatic attraction exists between one water molecule and another water molecule. Technically, it's just the oxygen of one and the hydrogen of the other. So it's always the oxygen of one, hydrogen of the other that forms the hydrogen bond, that attraction that exists between them, okay? It's not a permanent bond. It's just the alignment, how they align with each other. It's not even a permanent bond. It's just a temporary attraction. So this alignment actually is responsible for the anomalous behavior of oxygen and anomalous behavior of water. In other words, water, you must have seen how beautiful it forms those crystals, icicles, right? Water floats on like the ice floats on the water when it freezes, because the water expands when it cools, because it has to accommodate the hydrogen bonding, okay? Water also has very high boiling point. Why? Because of hydrogen bonding. You have to break these bonds, this network that exists between the molecules, in order for the liquids to boil. So if this network is existing and it's very strong, then it takes very long to break that network. So that's the deal with the hydrogen. Now comes the dispersion forces, hydrogen and water molecules. Now comes the dispersion. Now dispersion or London dispersion or Van der Waals, they are all the same. This is just a spread of the electron cloud. The electron cloud spreads overall. So by default, London dispersion forces are present in all the molecules. Okay, the rest we have to see which is the other more dominant force. Okay, so here, for example, here is a neutral, like a dipole. This is actually a temporary dipole comes in a non-polar molecule. So all non-polar molecules will have London dispersion forces or dispersion forces. So remember, the electrons are all the time moving. So they are moving even in the bonded state, they are moving. So when they are moving, what's going on? When they are moving, temporarily a dipole comes. And that's a very temporary shift because of the movement of the electron that brings the delta positive and the delta negative end. And then remember that it's the positive is always attracted to the negative. So the way they align in such a way that the negative and the positive, they connect to each other, okay? So that's the example of the London dispersion or the dispersion, okay? Now, keep a few things in mind that, where is that? Let's do this here. Yeah, melting point and the boiling point. The substances, you know, melting obviously occurs after something is a solid and it has, you know, gained enough of heat, and then it becomes, you know, liquid. Anyways, so you see here, all molecules will have dispersion forces, but particularly these will only have the dispersion forces. Chlorine and fluorine, only dispersion forces. So these are non-polar, right? The dipoles cancel out, non-polar. And if you look at it, fluorine is very electronegative, right? So chlorine is less comparatively. So that is why the melting point of fluorine is much lower than that of chlorine, okay? Next is, look at the dipole that exists between HCl and HBr. So what's the deal here? HCl and HBr. HBr less electronegative, HCl more electronegative. More polar, HCl is more polar, HBr less polar. More polar means that it's going to take longer for it to melt. It's going to, the intermolecular forces are stronger. They're going to stick more. So you need to provide more heat to melt it, you know, so those things. Next is the ammonia and water in hydrogen bonding. So yes, it's hydrogen bonding, you know, technically oxygen is more electronegative than ammonia. So the more electronegative oxygen will have a stronger bond with the neighboring hydrogens. Neighboring, it's always neighboring, okay? So that's the thing. And so we see that for ammonia also, but then I don't know why ammonia. Okay, anyway, so here you have magnesium fluoride and NaCl. These are ionic compounds. Very, very, like, it will take very long for them to boil, and then even more long, you know, for it will take long for them to melt, you know. So that's the thing, melting points. Okay, now let's look at these some other examples here. Look at the dispersion forces. Now, dispersion forces in fluorine, temporary dipole. So this is fluorine and fluorine, one and delta positive aligns to the delta negative of the other. So that's the alignment. And the thing is that because it's very weak interaction, this is a very, very weak charge. The charge is also not a strong charge. It's not separation of charge. It's just a temporary, you know, inducing of the dipole. So that kind of dispersion forces or you know, London dispersion. Okay, then comes the dipole-dipole interaction, like bromine and chlorine. Bromine, less electronegative, chlorine, more electronegative. That bond is a polar bond. So the positive end, that is the bromine end, gets attracted to or is aligned to chlorine of the neighboring, you know, and sometimes their bonds can also break. But nonetheless, this is the dipole-dipole attraction, and it exists whenever there are nonmetals. So this is how they look and or they align. Okay, next is the hydrogen bonding. So fluorine, oxygen, and nitrogen. Okay, so fluorine, for example, in this case, has a delta negative end, and hydrogen is the delta positive of the other. So it's the lone pair from fluorine that gets, you know, that connects with the hydrogen. So that attraction is there. It's not like the fluorine is giving away its lone pair, no, but bonding, that attraction is there. It's a very weak network between the hydrogen of one and the fluorine of the other. So because of that attraction, there's this network that it stays stable, and it influences the properties also. Okay, so that's one thing. Then comes the covalent bonds in general. When nonmetals combine, they are basically sharing the electrons. Okay, so that sharing of the electrons is, of course, going to make it strong. So chlorine bond is pretty strong bond. Okay, but if there is a separation of charge, we will see positive and negative ions. In the solid state, they remain pretty strong because they take very long to evaporate, to melt them. Their boiling points, melting points are very long, very, very like high. But sodium chloride, being solid and ionic, it's able to dissolve in water. So in aqueous medium, it's not a very strong bond, but in solid medium, yes, it is. Okay, so we see that as the molecules, as more and more attraction comes in the play, then the bonds become strong also. So hydrogen bond is a very strong bond, is stronger than the dipole is stronger than the dispersion forces. Okay, so now let's look at the problems here with these problems. So 81, 83, and 85. All right. So 81, major attractive force. So, you know, I like to draw the Lewis structures. That helps you. So nitrogen and fluorines. So nitrogen has 5 electrons, and fluorines, there is 1 nitrogen and there are 3 fluorines. Each is bringing 7 electrons. So we have multiply. So we have, sorry, let me just move this here. Okay, 7 3s are 21, and this is 5. Okay, so 26 electrons, and nitrogen, fluorine. All right. Okay, what is a major attractive force? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. Okay, so this is a polar molecule. This is a polar molecule, and the polarity is towards nitrogen side. Okay, and I'm going to do this later, BRF. So now, obviously, it's between, so it's not, so no hydrogen bonding here. Major attractive force here is still, I think, dipole, because is dipole. because nitrogen side, remember, anytime you have these lone pairs, that always brings out a polarity in the molecule. So this side is going to be delta negative, and then I wouldn't say that this side is positive, but it kind of cancels out the polarity. Remember, they are the three the same kind. So this is a dipole-dipole interaction here. And we will also see on the side a little bit of dispersion, or generally it's called a London dispersion forces. Okay, so LDF is there, dipole-dipole is there. All right. Next is that next one was bromine and fluorine. So you guys should do this the same way as I'm doing it. Let's move on to the next one. Strongest attractive force. So here, very clearly, you don't have to look at anything. OH. OH means that OH, the strongest will be hydrogen bonding. Anytime you see OH, it will be hydrogen bonding. Now, anytime you have carbon-hydrogen bonds, these are non-polar. And when they are non-polar, that means the London dispersion forces is only going to be, okay? And CH3 London, but there is no dipole-dipole, and there is no hydrogen bonding, okay? Now, next is which one has a higher boiling point, HF or HBr? Which one has a highest boiling point? For that, let's look at this one. Highest boiling point, HF or HBr. So HF, although HF and HBr, HF will have hydrogen bonding and HBr will not. So higher should be of HF, because hydrogen bonding takes the precedence. Hydrogen bonding really, keeps them, network is strong. So hydrogen bonding is present. So HBr is just dipole. So dipole. So we see that hydrogen bonding is stronger than dipole-dipole, and dipole-dipole is stronger than London dispersion. Okay, so this is the thing, and that because of that, the HF will be, the boiling point should be higher. Okay, next is methane, or which one has a highest boiling point? Once again, OH. Anytime you see OH or NH or HF, hydrogen bonding. So anytime there is a hydrogen bonding, that means that will always increase the network. So this will have a higher boiling point. All right. Okay, so this finishes the homework, and I have done the important questions, but you guys should also do more for practice. Okay. All right. Thank you for watching. Bye-bye.